So welcome everyone to the continuation of the Europractice 2D EPL webinar series on graphene. Some of you might have remembered that 2 years ago, it's already 2 years ago, that we started this series with first an introduction to graphene. So that was myself together with Daniel Neumeier from AMO. Then we continued with some more details on the graphene-based devices made by AMO. So that was Gordon Rinke who gave the webinar. And then the last webinar in the series at that time was by Mika from VTT, and he focused in more on sensor CMOS integration. But today we continue the series. So you will see later on a nice presentation from Graphenea, more specific by Elias and Juan Manuel, who will highlight you the Graphenea process on passivated contacts, hafnium oxide backgates for really versatile device architectures. So before I give the floor to Elias and Juan Manuel, I would like to introduce them. So Dr. Juan Manuel Gomez is a solid-state physicist from the Complutense University in Madrid, where he finished his master's in 2015. He later joined the Nano Devices group of CIC Nano GUN in Spain, where he completed in 2020 his PhD on spintronics, studying the transport of spin information through magnetic insulators. With over 8 years of experience in clean rooms, device design and fabrication, he joined Graphenea 3 years ago as a process engineer, and now he is part of the integration and yield team. Following, Dr. Elias Torres is also a solid-state physicist by also the Complutense University in Madrid. Right after, he spent 1 year working on antimony-based nanowires grown by MOCVD and Lund University in Sweden. And then in 2014, he went to the UK to carry out his PhD in the Graphene Engineering Center within the Quantum Systems and Nanomaterials Group at the University of Exeter. His thesis was on scalable process methods to integrate 2D materials into semiconductor workflows. Then he obtained a Marie Curie grant to come back to Spain, and he arrived at Graphenea, where he now leads the process integration group. So without ado, I would now like to give the floor to both Elias and Juan Manuel to introduce the audience to what Graphenea can do for the Europractice community. The floor is yours.
Thank you, Romano, for that kind introduction, and thank you everyone for joining us in this webinar. Thank you to the experimental pilot line as well to give us the opportunity to present this novel process flow and make the people aware of this device architecture. So I'm just going to show outline of the talk. I'm going to be talking about the 3 bullet points, warming up the floor for my colleague Juanma for the main act. So we're just going to introduce graphene very briefly, since we assume that most of the people attending have some experience of some background of some kind in graphene. Then I'm going to be talking about some applications and markets as well that we target or you can take advantage of with this novel process flow. And then I'm going to be introducing Graphenea, introducing us. And then I leave the floor to my colleague Juanma, so he can go through into the details on this multi-project wafer run and wrap it up with a summary. So yeah, let's get into it. So yeah, graphene, it is a carbon allotrope, right? You have other allotropes, carbon nanotubes, fullerenes. Graphene is really a monoatomic layer of graphite, and thus it has a strong in-plane sigma bonds, which make them really strong in-plane, but weak van der Waals out-of-plane interactions, which make the possibility of exfoliating, and also this truly monoatomic dimension or character make it a really flexible material as well. And these characteristics indeed sparked a lot of interest, more than a decade ago, because we were reaching, the limits of we are reaching the limits of miniaturization. So indeed, a material that has an ultra thin body that doesn't get affected by roughness scattering, and this monatomic dimension also provides good electrostatic control. And more importantly, what people saw is that there was no mobility degradation when you introduce aggressive scaling in these devices, in these 2D materials. So it indeed sparked a lot of interest due to the potential to extend the Moore's law for longer. To give some characteristics, so graphene is what we call a gapless semiconductor. So it has both conduction bands and a valence band that they touched at the so-called Dirac point, and here's the minimum conductivity. It has a high carrier mobility, so typically in excess of 1,000 centimeters squared per second. But at cryogenic temperatures, if you encapsulate it with boron nitride, you can reach hundreds of thousands or even millions of centimeters squared per second. About the optical properties, so graphene is optically transparent. It absorbs 2.3% of light, and this absorption is quantized per layer. So you can see that as you increase the number of layers, the absorption of the device is increased. And precisely because it has a linear absorption, it has a flat absorption as well in a wide range of wavelengths. So pretty much from 450 all the way up to 700, the absorption is flat. So you don't need to compensate with electronics or different mechanisms to supply for these different absorptions. Regarding biosensing, for instance, it is a pure carbon material, so it is truly an organic material. So people can take advantage of the whole plethora of carbon functionalizations and to really anchor and functionalize the surface of this material with the biomolecules. And due to the monatomic character of the material, it has a surface to volume ratio of 1. So it is really the ideal material to build sensors or sensorics. The drawback is that it needs sensitization or functionalization to provide this specificity. Compared with other allotropes that we've mentioned before, or with other emerging schemes such as carbon nanotubes and nanowires, graphene is a 2D material, so it has a planar structure. So the semiconductor manufacturing techniques that are used in semiconductors workflow, lithographies, etching, metallizations, they can be readily translated to graphene. So we don't need to invent novel process flows or novel schemes to contact these unidimensional materials or architectures. And indeed, being able to manufacture these devices at wafer scale with these miniaturization approaches, it really allows to take advantage of the economies of scale of semiconductor manufacturing and really drive the cost down of these devices when you go for high volume manufacturing. So having introduced graphene, let's talk about a bit of applications and markets. So we have identified two industries slash fields in which graphene can really add value to. So the first one is biosensing and healthcare. Um, Interestingly, you're dealing with aptamers, antibodies with fluids. So in this case, the geometries that and the designs that the devices require are quite relaxed. Indeed, these devices are usually built in the order of microns, so no aggressive scaling is needed. And precisely because the level of integration that is needed for these components is low, you don't need PDKs in the sense of EDA tools or CAD tools, right? With simple physical design, you can get very good devices and useful devices. In this case as well, there's no ultra high mobility needed. So for sensorics to have a good limit of detection, you don't need 10,000 centimeters squares per volt per second, because it's really the monodimensional nature, this surface to volume ratio, what provides this high sensitivity. A lot of people have been very much worried about the hysteresis in these devices, but in this case, hysteresis might actually be beneficial because it may be used as a sensing parameter. We have customers that actually prefer to have hysteretic devices rather than non-hysteretic devices, because that is a parameter that they use as a KPI in their analysis. As I mentioned before, these devices are very sensitive, but you need some sort of functionalization to provide this specificity. There's a vast library of biorecognition elements, so antibodies, aptamers, nanoparticles, really anything that is being used at the biosensing level with other techniques, I don't know, surface plasmon resonance, lateral flow devices, they can be readily adapted to this approach. And indeed, all these features enable, point of care applications, which, since the pandemic, a lot of people are trying to improve these diagnostic tools in a point of care fashion. So an example that we like to illustrate this with is a typical electrochemical sensor versus a GFET sensor. So a typical electrochemical sensors, the measurement depends highly on the counter electrode, the reference electrode, and the working electrode. And indeed, these are difficult to miniaturize because you need certain area to be able to drive, certain current. So the miniaturization is difficult in these devices. So the cost effectiveness comes actually from the manufacturing. So usually screen printing techniques, roll-to-roll techniques are used to manufacture these devices, which cannot really compete with the semiconductor manufacturing techniques in terms of reliability and process control. In comparison with the GFET, the measurement only depends on the aspect ratio of the device. So, if you have a 1 by 1 millimeter device or a 100 by 100 millimeter device, the device should behave the same. So the miniaturization of these structures is readily available. And this implies a dramatic cost reduction without losing performance, which very much eases the introduction or the translation of these prototypes into actual mass-produced technologies. The second example that I would like to mention is, the second industry / fields is optoelectronics and photonics. As I mentioned previously, so one advantage of graphene is that it has a flat absorption. but indeed this absorption is low. We're talking only about 2.3%. So these devices really need to be sensitized for both absorption and specificity. So what most people do is anchor or deposit quantum dots, perovskites, organic molecules that create the function of both being more absorbent than graphene itself, but also provide a specificity to a certain wavelength. So with the case of quantum dots, one can tune both the material but also the quantum dot size to really match whatever wavelength you're interested in, and really, you know, be deposited on top of these field effect transistors to provide it that specificity. Then you have these, you know, because you combine a material with low mobility, such as, you know, quantum dots and organic molecules, with another material with high mobility, you have this photogating effect, which provides indeed a high responsivity. So it provides, you know, good photo detectors, sort of say. Indeed, the possibility of using you know, low equivalent oxide thickness dielectrics or high K dielectrics enable the low power operation of these devices. So why we think that this MPW is important and who is really driving this graphene market? So this is a plot I extracted from a paper that was published, I think maybe like 3 or 4 years ago, from a few members of the flagship and other scientists, where they analyze, you know, the market opportunity versus the kind of like complexity of the process. So what we've seen in this, you know, over a decade that we've been in the graphene business, is that it is actually startups and SMEs who are driving the market really, and really with niche applications at the back end of line, which, you know, it says low complexity. I wouldn't call them low complexity because they're still pretty complex devices, but indeed the level of integration that they require is definitely, you know, of a different level that you need to create, you know, a full microcontroller or microprocessor. So we think that there indeed, you know, opportunities in sensors and photodetectors, which are going to be driving the market in with these graphene structures. And these are really the two fields that we are targeting with this MPW. So as Homa will explain in a minute, the structures that you can build with this novel process flow are mostly sensors and photodetectors which match this this low tail of the roadmap. So yeah, we think that this MPW is going to be relevant for the startups and SMEs that want to, you know, prototype some devices, some sensors, some photodetectors, which within this architecture is very much suited for. So let me introduce us very briefly, Graphenea. So we were founded in 2010 in Donosti, San Sebastián in Spain. We have, you've been lucky enough to visit us or visit San Sebastián. You know that we're known because of the great beaches and the fantastic food that we've got around here. We're a spin-off from CSC Nanogune. We are currently around 30 people with over 70% of the staff women, and we are really a multidisciplinary team. So Juanma and I, we're both solid-state physicists. We've got chemists as well, engineers, biotechnologists, really to have this multi-angular approach to problem solving and application development. We're also a member of the Graphene flagship and of course of the 2D EPL. And just to mention, an overall picture of where we are. We have a strong presence in Europe and USA. I would say that roughly 80-85% of our customers are based either in Europe or in the US. But we're starting to have an emerging presence and started to build a reputation in Asia, more specifically in the Japanese market. So we have currently 300 square meters of clean room ISO 6.7, where we offer vertical integration of graphene. So we control the growth of the graphene, which we grow on copper foils by CVD. Then we transfer onto wafer substrates, so we can process from really centimeter square samples all the way up to 200 millimeters. We have extensive experience working with silicon and silicon oxide, but we have also experience working with nitrides, with arsenides, with phosphides. If it's wafer shaped and flat, there's a high chance that we can transfer onto it. And then we have also the processing of these films. Processing we carry out currently at 100 and 150 millimeters, and we're gonna upgrade the processing as well to 200 millimeters very soon. And we can build pretty much the whole plethora of electronic devices. So we can build resistors, we can build diodes, transistors, hall bars, or TLMs. I would say that we can build pretty much any sensible device that you can think of. So I leave the floor to my colleague Juanma. So he's going to be talking to us about this specific multi-project wafer run. So Juanma, go for it.
Okay. Now after this introduction about the graphene and Graphenea, I'm going to focus about this new novel process flow that we are going to show in this 2D EPL. As you're gonna see in the whole presentation, we offer a versatile platform for different type of devices within one process flow. This process flow has different architectures. That's why we say that it's versatile. We are going to use hafnium oxide as a dielectric because hafnium oxide has a large capacity coupling for low voltage operation for the devices, as Elias said before. And I'm going to show along this presentation different devices that we can build. For example, two terminal devices with or without encapsulation, or as well 3 terminal backgate devices also can be or not encapsulated. And the last devices that I'm going to show is 4 terminal devices with local heaters. This multi-project wafer run will have 6 steps during the device fabrication. The first step is going to be the alignment marks for the whole process because we use photolithography process. In this alignment marks step, we can also use deposit the backgates or the heaters. After that, the second step is going to be the dielectric deposition of hafnium oxide. Then the wafer, we will have the graphene transfer and the and later on the graphene patterning. Then we will evaporate the contact for the graphene, and we will finish this this multi-project wafer run with the aluminum encapsulation. Let me start with the first devices that we can build. Are the 2 terminal devices that we can offer with or without encapsulation. We have the silicon or the oxide substrate with the 40 nanometers hafnium oxide on top. where we transfer the graphene patterning and we will have the contacts. These devices, well, we also can do a whole bar geometry, and these devices can be used for gas sensor, biosensing, magnetic sensor, or carrier transport. With these kind of devices, if we do a scratch in a corner to access the silicon in the backside, we can also do 3 terminal devices with global gating. These devices are important for because if you decorate them with quantum dots, perovskites, or organic molecules, can be used as a photosensors. With these terminal devices, we can also do liquid gating. For example, here we have an S20 that we can offer, where this contact is a local gate. Through this local gate and the graphene structure that we have in the device, we can do the liquid gating. These are important devices for biosensing. But we can also use 3 terminal devices for local gating. For example, here we have a back gate and separated by the dielectric to the graphene. For example, in this picture, we have the back side here is the dark side. Then we have the dielectric, and these are the source and drain contacts for the graphene. These 3 terminal devices with local gating can be used for photodetectors, optical modulators, but also for magnetic sensor and biosensing. The last devices that we can do is this example is a heater that we have in the backside, then the dielectric and the graphene on top. This heater can be used, for example, for gas sensor, for the gas desorption. When you detect the gases, you can heat the device to use it again. More in detail, what we can offer in this multi-project wafer run, we will have a backgate metal with titanium gold 515 nanometers, you can see here. Then we will deposit the 40 nanometers of hafnium oxide on top, the transfer of the graphene, as Elias said, CVD grown with over 97% monolayer. And then we will perform the pattern and the metal source drain contact that is gold-based 50 nanometers. And then the last step is going to be the passivation of with the electric of alumina that can passivate the whole device or only the contacts. We have some design rules for this multi-project wafer run. Here we saw some of them are quite easy to follow, and what we have also is a GDS file in K-Layout. Well, K-Layout is a free software that you can use, where we already designed a P-cells that here you have, for example, for types of devices with a heater or with a bottom gate with different size for the graphene. So this is just for the customers to be to help them to build their own devices. Based on our experience in the process flow 1, we also have some recommendations about the graphene channel. For example, for devices with a width below 20 microns, we recommend use aspect ratio of the channel over 4 times. Or, for example, for devices bigger than 100 microns, we recommend just 1/1 the aspect ratio. The possible architectures that we can fabricate in this multi-project wafer run are, for example, what we call device A, that is the full process. We have the silicon oxide with the backgate, the dielectric on top, and the graphene. Here we have the passivated electrodes, the graphene channel is open, and we have the backgate or the heater, depends of the preference. One variation of this device B, is the same procedure, but we don't have the backgate at the bottom. But still we have the passivated electrodes and the graphene channel open. The last device that we can fabricate in this novel process flow is with the backgate and also the graphene passivated. In this case, both the electrodes and the graphene are passivated. Now I'm going to talk about possible applications of the different devices. For example, device A can be used for gas sensor, biosensor, or for the detector. As an example, here I show you a collaboration that we did with Kairos Sensor, where they use our devices and they decorated them with perovskites. And what they saw is that they increased the X-ray detection signal to noise ratio from 30 to over 200. They use this for imaging, medical imaging. And another important thing that they saw is that these devices were reusable. They could wash it and deposit it again, the perovskites, and the device still works. And they could use it for several times, which is quite important. For the device B, we have other applications, for example, biosensing and photodetector. And in this case, I'm going to show a biosensing example. This is also a collaboration with the Imperial College of London, where they develop a point-of-care diagnostic tool for early disease detection. They develop a portable biosensor that can detect pancreatic cancer from a blood plasma within 45 minutes, which is pretty fast. In this case, they use the direct point position to detect or difference between the healthy plasma and the cancer plasma with pretty nice accuracy. The last device that I'm going to talk is this C that can be used as optical modulators, magnetic sensor, or carrier transport. In this example, the devices were completely encapsulated, and the results were that 75% of the devices show low doping and almost negligible hysteresis, which can be very important, for example, for devices for doing Hall sensors. Okay, now I'm going to show you a device with the full process. For example, here we have an example with 3-terminal device with local gates. We can see here the local gates, and these are the passivated electrodes of the graphene. And on top of this local gate, we have the graphene channel open. Another example is the 4-terminal devices. Again, we have the heaters at the back part, the passivated electrodes of the graphene, and the graphene on top. Actually, in this zoom image, you can see the graphene encapsulated at the bottom. After the whole process of the multi-project wafer run, we have some dies to do the quality control. Our quality control is based on AFM measurements for the roughness of the devices and the graphene. We also perform the Raman to see the intensity ratios and the G position and the full will have maximum. We also perform the transport characterization for the mobility, direct point, and hysteresis measurements. And optical microscope to see the channel integrity is over 95%, and the device yield is over 75%. So I hope that I convince you that this process flow is versatile, that we can build 3 different kind of devices, and depends on the application that you want to use. To finish, I will encourage you to apply to this multi-project wafer run through the Graphene Flagship website. The call is already open, and the deadline is end of June, 30th of June. Well, if you have any doubt, of course, here you have our emails to contact us for any technical question or any doubt that you have. And I would like to also to add that a couple of weeks ago, it was announced that Graphenea joined Europractice. So also our multi-project wafer runs can be are also now in Europractice. We will start in August with the Graphenea Process Flow 1. Well, you can check it now already in the Europractice website. So with this, I will like to thank all of you for your attention.
Thank you.